to integrate. We're trying to find the volume of this cardioid thing, right? So it's like going, and we have parameterization. X equals cos theta, 1 minus cos theta. Theta is going from 0 to 2 pi. Y is sine theta, 1 minus cos theta. Okay, I mean, I guess it's nice to know where some of these points are as well. Okay, the problem is to rotate it about the axis and find the volume. Okay, and this can be found in Terry Lee's book at the end of the volumes chapter. Okay, so to find some of these points, you might want to say let x equals 0. You know, so if x equals 0, then cos theta equals 0 or 1 minus cos theta equals 0. So theta is going to be pi over 2, 3 pi over 2, or 0, right? And it could also be pi. So this could be pi over 2 or 3 pi over 2. And this is 0. Okay, so there's 3 points for which there is 0. And so you kind of see already, like, if you're going to do volumes by rotating a disk, right, you're going to start getting problems when you get to here. So let's just pretend we're going from here to here for now. And you can also kind of see, like, as theta, so if theta is 0, you know, x is 0, so it's starting here. Well, when you put 0 here, y is 0, so it's starting here at the origin. And as you increase it, I mean, you know, this thing is positive, and this thing's positive, so it's going to be positive y, and it's going to be positive x, because for acute angles, this is always positive, and for acute angles, this is positive. So it's going to do something. So this is doing that until pi on 2. Okay, so then this is from theta equals pi on 2 to theta equals, so the next time y equals 0. You know? So the next time y equals 0 is when either sine theta equals 0, which you said it was 0 or 2 pi. And that's corresponding to the starting point. But then although when this is equal to 0, when cos is equal to 1, I did something wrong. So cos is equal to 1. When yeah, so I guess we didn't quite find this point here. So when y is equal to 0, sine is either equal to 0, which makes this 0 or pi, yeah? Yeah, 0 or pi. And because this is only 0 when theta is equal to 0. So then it looks like we're trying to integrate from pi on 2 to pi. Yeah, so I guess it goes from 0 to pi on 2 to pi to 3 pi on 2 to 2 pi, yeah? Okay, so then this is y now, right? This is dx. So our little volume of the disk will be pi y squared dx. We'll put the limits in later, okay? And then, y squared was sine squared theta times 1 minus cos squared theta, right? Sorry.
Yeah.
1 minus cos theta squared. And then we have sort of x d theta. And this is kind of the point where we're integrating y squared dx. But sort of the only thing they have in common is theta. Yeah? So we go dx d theta is minus sine theta. 1 minus cos theta. And then sine theta. Cos theta. Right? Okay, so then the integral we end up with after substituting for theta is something like this. So the volume of this part here, let's call it V1, right? So sine squared theta 1 minus cos theta squared times this thing. So there's a sine theta we can maybe let's just write it. Yeah. Okay, so I guess at this point, instead of kind of finding the exact value of the integral, let's just be convinced that it's integrable. Okay, so if we were to expand this, so maybe we can make it a little bit more obvious how it would look when we expand it. So let's just expand it a little bit more, yeah? This is pi somewhere there. So this here will be a sine squared theta, and this will be a minus 2 cos theta, right? The last thing will be a cos squared theta. And then in the other brackets, it's minus sine theta plus sine theta cos theta. So it's plus 2 sine theta cos. Okay. Alright, so what kind of terms do you get? Let's write them down. So you get a sine squared times this, right? You get a sine squared times this. So you get a sine cubed. Yeah? You get a sine cubed times cos. We'll just ignore the 2. You get... Oh, maybe you could put that 2 back in with this. Okay, so then you get another sine cubed cos, right? So we have nothing new. And then you have a sine cubed cos squared. Right. And then you have, so there should be 6 terms. We have 3 of them, or 4 of them. One of them just repeated. and then this is cos squared sine cubed, right? So that's already there. And then this last one is cos cubed sine cubed. Yeah, and assuming they don't cancel, it would suffice to just say each one of these were integrable to show that the whole thing's integrable, right? I think you already said you could do something like this one pretty easily, right? You just substitute for cos, because the derivative of sine is cos, so you have that. Can you see how to do some of the other ones?
I can see how to do the bottom one, but not so easily.
Yeah, so the bottom one is kind of the same as the first one, right? Because the bottom one is like a sine, it's like a sine 2 theta cubed. Yeah. So the bottom one is related to the first one. So if you just wrote this as cos theta sine theta cubed, right? You get like half sine 2 theta, and then it's cubed. So the 2 we don't really care about, so it's really the same as sine cubed theta, yeah? Okay, good. And I think these two will be the pretty similar principle. Can you see, like, if you put a sine theta out here, right? The sine squared just becomes 1 minus cos squared. So then it's a similar situation of this, because the sine and cos are derivatives of each other. And here it's the same thing. You take so whenever there's an odd power, basically, the sine comes out. This turns into a cos, and then you use the sine to make it into like make cos into x, and so then you can do all four. Yeah. Okay, great. So that's like so we're convinced that we can find the integral of this. Okay. So let's stop there, and then let's see. So that's from here to here. Okay. Okay, but what happens sort of on the other side? I'll give that a go.